Far in the distant past, and predating the first civilization by hundreds of thousands of years, when our ancestors looked up into the sky and beyond the clouds, three things were always there at one time or another: the sun, moon, and stars. These three entities dominated the sky day and night, just as they do now. Over time, the realization of the usefulness of the sun meant that early humans could easily rationalize its existence. For the moon, its periodic phases were eventually linked to recurrent events on Earth, the most important one being the seasons. Early humans also used the phases of the moon to plan the time to hunt and also plant crops. For the stars, things were a little bit different. At first glance, they appeared to be just static points of light in the night sky. But it didn't take long before early humans started to detect patterns in the placement of these points of light. More importantly, these patterns moved across the sky just like the sun and the moon. Naturally, these patterns became a useful way to keep track of time, especially the seasons. They were eventually personified to reflect the beliefs of many cultures. These patterns then became useful for navigation over great distances. Despite the fact that these points of light, or to be more specific, stars, were useful in so many ways, they remain nothing more than just visible points in the night sky. Some ancient cultures even thought of the stars as patterns that were sewed into the fabric that was draped over the earth to create night each day. As ancient philosophers studied the night sky, the way it was viewed began to change. Stars were no longer sewed into a veil called the night sky. There was no veil, just stars. Points far away that emit light. Some even suspected that these stars could be suns that are far away. They had no real proof for this claim. But over time, as philosophers became scientists and technology improved our instruments, we were able to measure the distance to a star in 1838. This was a big deal because it was now possible to show that the stars are as bright as our sun when at a close distance. Stars were no longer just points of light, but points of interest. There were potentially hundreds of thousands of things to study in the night sky, but it wasn't until 1933 when we first detected invisible electromagnetic waves in the form of radio waves coming from the Milky Way that we realized that there were activities everywhere in our celestial sphere. This is the Orion constellation, one of the most recognized constellations in the northern hemisphere. In ancient Greece, Orion was seen as a strong hunter, which after his death by an arrow from Artemis was placed in the heavens by Zeus. In some interpretation of the constellation, Orion carried a bronze club in one hand and a shield in the other. In the middle of the constellation is the belt, or even the arrow that killed him as some see it. While this arrow may have caused the death of Orion in ancient times, right below this belt is something that in modern time is seen as the giver of life. Below the Orion belt is the Orion Nebula. It's a large stellar nursery, a place where stars are born. Look at a star, and what do you see? A point of light. What can we say of that star? Nothing much besides it being a point of light. If we look at a few stars, we'll notice that some are brighter than others. That could tell us something about the star later. When we look at even more stars, we'll notice slight color changes from star to star. Now, that's definitely interesting to note. But that's about it as far as the information that we can gather from the star with our naked eyes. This information could roughly be translated into relative size, or maybe distance, or maybe temperature of a star. Not very useful, but definitely allows us to start categorizing these points of light in the night sky. But lucky for us, in the early 1700s, Sir Isaac Newton made a discovery that would lay the foundation for a class of scientific instruments that would dramatically increase the amount of information we get from the light coming from the stars. Newton discovered that when sunlight passes through a prism, it is split into its constituent colors, or the visible spectrum. Passing starlight through a prism and getting a visible spectrum didn't give us much additional information about a star. At first. Not until 1814, when Joseph von Fraunhofer, a German physicist, studied the visible spectrum of the sun in detail. He noticed that there were many black lines that ran vertically on the light spectrum that came from the sun. He identified over 570 of these lines and gave each line an alphabetical identifier. However, the cause of these lines were unknown. 45 years later, two German scientists, Gustav Kirchhoff and Robert Bunsen, discovered that some of these black lines were in the exact same position as the emission lines of the spectrum created when the light of chemicals heated to the point of incandescence or electric discharge is passed through a prism. When chemicals are heated to incandescent, they will emit light only at certain frequencies or colors. When passed through a prism, these frequencies will show up as lines of colors instead of a continuous spectrum. These lines are called emission lines. So, because these emission lines matched some of the black lines which Fraunhofer discovered, Kirchhoff and Bunsen concluded that they were absorption lines. Absorption lines are created when white light is passed through a gas. The gas will absorb certain frequencies of the light, creating dark lines in an otherwise continuous spectrum. The frequency absorbed are dependent on the element of the gas. This conclusion suddenly made it possible to detect some of the elements that are present in the sun, and by extension, some of the elements in a star. Suddenly, we are now able to extract more information from starlights than ever before using these black lines, which are also now called Fraunhofer lines. Using the Fraunhofer lines from tens of thousands of stars, we were able to classify these stars in ways that further our understanding of them. For example, the Hertzsprung-Russell diagram plots the relationship between the luminosity and temperature of a star. The temperature of the star is derived from the characteristics of those Fraunhofer lines or absorption lines. These include the width and intensity of each line. Since these lines are absorption lines, they tell us about the composition of the surface of these stars. The width and intensities of these lines are directly related to the temperature of the gas on the surface of the star. Now, when we plot these temperatures against the luminosity of a star, we get a distinct pattern. We're able to derive all of this information just from the little amount of light we receive from the stars. Slowly over time, we were able to piece together the life cycle of stars from this pattern. A cycle that can span billions or even trillions of years. Considering that the lifespan of an average human is only about 75 years, it is amazing that we're able to derive detailed information of the very long life cycle of stars. Astronomy by necessity is a science based mostly on remote observations. This makes it very difficult to get information about the items under investigation. In this case, stars. Excluding the cyclic motion of the moon and planets, at one time in our distant past, the heavens, or space, and everything in it was thought to be static. There was no reason to believe otherwise because that's how things looked, even today, if we were to look at the night sky with our eyes for a decade straight. But with instruments, we did notice important differences between stars. And in our attempt to explain those differences, we realized that things did change in the night sky, but it didn't take decades, hundreds, or even thousands of years. It took millions of years. But how did we come to this conclusion, especially considering that our recorded history goes back only about 5,000 years? This is where the night sky gives us a break for a change. Things may change very, very slowly in the night sky, but there are very, very many things that are changing. Imagine an alien from another planet landed on Earth and only had one day to analyze humans before returning home. That's too short of a time to see any development in humans. However, after analyzing tens of thousands of humans, they will figure out the general life cycle and other developmental changes in human beings. This is possible because at any given time, all of the different developmental stages of humans are active in the billions of people that are alive at that short instant of time. From babies to the elderly, it's all there. The only thing that remains is to figure out how these various stages properly connect into a life cycle. The same thing is true for stars. 100 years is an instant in time for a star. But when we look into the night sky, we see stars in various stages of their life cycle. The stellar life cycle, from protostars to neutron stars, black holes, and white dwarfs. It's all there in the night sky. We're able to make these determinations in part because of the spectral analysis of the visible light coming from the stars. We know that there are trillions of stars in the universe emitting light, but there are many times more celestial objects that do not emit light. Interstellar clouds, planets, and asteroids are all celestial objects that do not emit light, at least not visible light. So how can we know anything about these objects when they are light years away but emit no light? Let's momentarily go back in time to the year where an important fundamental discovery was made. In 1800, Sir Frederick Herschel, a British astronomer, was analyzing sunlight through a prism. Specifically, he was measuring the temperature of each color in the spectrum. He did this by placing a thermometer over each of the colors created by the spectrum, from violet to red. He noted that the thermometers that were placed over each color were all showing higher temperatures than the thermometer that was not exposed to the spectrum at all. When he then placed a thermometer just outside of the red color of the spectrum, expecting to get a lower temperature than the ones inside the spectrum, he got a temperature that was higher than any other temperature taken from inside the spectrum. He just discovered for the first time light, or radiation, that the human eye could not see. He called this radiation calorific rays. Years later, these calorific rays would be called infrared rays. Infrared rays are sometimes called heat rays because they are emitted by every object that is above absolute zero. Objects that are below 1000 Kelvin or 727 degrees Celsius, but not near absolute zero, emit thermal radiation that is practically only in the infrared. This means that things that are not hot enough to glow visibly can still be detected if we were able to detect the infrared that they emit. This was challenging for a long time, especially since the infrared rays coming from space were very weak due to the vastness of space. But over time, scientists and engineers were able to build better detectors, and starting from the 1950s, we were able to reliably detect infrared rays originating from space. Now we were able to study other celestial bodies such as cosmic dust, planets, and gas clouds that are hundreds of light years or more away. These bodies, because of their great distances from Earth, would otherwise be invisible to visible light telescopes. The number of points of interest in the night sky once again went up by at least an order of magnitude. Among the many things that we are now able to detect, cosmic and interstellar dust proved to be very useful in furthering our understanding of the universe and how stars and galaxies are formed. Cosmic dust is dust from planets, asteroids, comets, moons, and even stars. And because of this very fact, cosmic dust can be found just about anywhere in the galaxy and even between them. Before infrared astronomy became viable, cosmic dust obscured the view of telescopes looking deep into the night sky. Cosmic dust clouds that are between Earth and a distant group of stars are able to greatly diminish or even totally block the visible light coming from these stars. The dust cloud is able to block the starlight not by necessarily absorbing it, but instead scattering so much of it that very little, if any, reached the Earth. Interestingly, the amount of scattering done by the dust cloud is dependent on the wavelength of the light that's passing through it. The longer the wavelength, the less it is scattered by the dust cloud. So, while visible light can hardly get to the dust, infrared, which has a longer wavelength, can easily get through the cloud. For the first time, astronomers were now able to see what's behind the massive dust clouds scattered throughout the universe. The core of many galaxies could now be studied in greater detail because the infrared light from the stars located there easily got through the dust cloud. This brings us back to Orion's belt and the Orion Nebula. In visible light, we clearly see the concentration of stars and the small amount of glowing gas surrounding them that's lit by these stars. Now, in the infrared, it becomes clear that this cloud is much, much bigger and is being surrounded by many, many times more stars that's causing it to glow. The size of this cloud is bigger than the entire constellation of Orion. In addition, based on how the dust cloud filters the infrared rays, we are able to estimate the average particle size of the dust. We are also able to determine to some extent the composition of the dust by passing the infrared light through an interferometer. An interferometer helps us graph the incoming light based on wavelength versus intensity. The graph created is a unique signature that can be compared against graphs taken from the infrared emission of known materials. One of the most amazing discoveries made by infrared astronomy is the discovery of the biggest ring around Saturn. This ring has a diameter of 300 Saturns lined up side by side. They were discovered because of the little but detectable heat they emit relative to their surroundings. We've also discovered many astronomical phenomena like astrophysical jets and brown dwarfs. Astrophysical jets are high-speed ionized matter emanating from a celestial object like a star or galaxy, while brown dwarfs are celestial bodies that are smaller than the smallest stars, but bigger than the biggest gas giant planets. Most of the heat generated by the brown dwarfs comes from gravitational contraction of the body itself. The more sensitive our infrared instruments become, the more they need to be in a highly controlled environment. The infrared detector on the James Webb Space Telescope, called Mid-Infrared Instrument, or MIRI for short, is an infrared camera that only operates at 7 degrees Celsius above absolute zero. In addition to that, it needs to operate above the Earth's atmosphere in order to prevent the very faint infrared signals that it detects from being absorbed by Earth's atmosphere. Our atmosphere absorbs a good portion of all radiation coming from space, but some frequencies are absorbed less than others. This fact led to an important discovery that was made in 1932.
Ready
Karl Jansky, an engineer with Bell Telephone Laboratories, was trying to identify possible sources of static that might interfere with the radio telephone service of the company. After building a specialized antenna and categorizing the static noise, he noticed that a faint hiss would occur every 23 hours and 56 minutes. This is exactly the time it takes for the Earth to rotate around its axis relative to a distant star. This is the length of a sidereal day. This indicated that the source of the static was most likely coming not only from space, but outside of the solar system. It turned out that the static was coming from the center of our galaxy, the Milky Way. And suddenly, once again, a whole new field of astronomy was born, the field of radio astronomy, with the possibilities of detecting vast range of new celestial objects and astronomical phenomena. When we think of observing stars and planets with a telescope, we immediately think of a cloudless night sky. That's because in the daytime, light from the sun is scattered everywhere in the sky, drowning out the light coming from the stars. On the other hand, clouds in the sky obstruct light coming from the stars. These obstacles to observation apply to visible light coming from space, but not to radio waves coming from space. And this gives radio telescopes, which are really large antennas, a nearly continuous observation advantage, day or night, rain or shine. This in turn made it easier and faster for radio astronomical observations to be made. In these observations, many new astronomical objects were discovered. One of the most notable is a pulsar. A pulsar is a highly magnetized rotating neutron star that emits a narrow beam of electromagnetic radiation, like radio waves. They first appear to be pulsating because they are only visible when the narrow beam that they emit is pointing in the direction of Earth, while in fact the beam is continuous but rotating with the pulsar. The fastest spinning pulsar spins at nearly 43,000 revolutions per minute. That's faster than the rotational speed of a jet engine on commercial airliners. It's a little less than 16 kilometers in diameter, and its mass is a little less than 2 times the mass of the Sun. Another great discovery by radio astronomy is the discovery of radio galaxies. A radio galaxy is a galaxy with giant regions of radio emission extending well beyond its visible structure. The radio emission is the result of the interaction between powerful astrophysical jets emanating from the galaxy and the surrounding medium. The jets originate from the core of the radio galaxy and is made of high-speed ionized matter. Some of the matter in the jets even approach relativistic speeds. As these high-speed ionized matter leave the radio galaxy, they collide and interact with whatever matter is in the vicinity. The interaction will either change the speed or direction of the ionized matter, causing them to emit radio waves. One of the biggest contributions to science from radio astronomy was finding physical evidence that supports the Big Bang theory of how the universe originated. This evidence came in the form of the cosmic microwave background, or CMB, a radiation that comes from everywhere in space itself. CMBs are photons that were created around the time of the Big Bang event from the hot plasma that existed at that time. As the universe expanded, the hot plasma cooled, and at some point, photons were no longer being scattered by the plasma and were able to travel freely everywhere through space. Over time, as the universe continued to expand, the photons that were created during the Big Bang event became less energetic because of the continuous expansion of the universe and space itself. The wavelength of these photons shifted from a short wavelength that includes the visible portion of the electromagnetic spectrum to a longer wavelength in the radio wave portion of the spectrum. Now we're able to detect these using radio telescopes and specialized spacecraft. The CMB is allowing us to study the state of the universe not too long, relatively speaking, after the Big Bang. It's also helping us study how and where galaxies are formed. It's quite clear now that everywhere we look in the night sky, there is some interesting object or some interesting phenomenon happening. Even if we observe only in the visible spectrum, a tiny patch with no stars is probably filled with thousands of galaxies when we look at it with a powerful telescope for a longer period of time. This was the case when the Hubble telescope took a picture over a period of 10 days targeting a small patch of sky. The patch was so small, 2.6 arc minutes to be exact, that only a few stars from our galaxies were in the frame. Yet, after the 10 days of operations were over, Hubble had captured enough light to create an image that had thousands of galaxies. This image is the Hubble Deep Field. All of these galaxies are located billions of light years away, with some being as far as 12 billion light years. We are seeing these galaxies the way they looked billions of years ago. The Hubble Deep Field is an image of the early universe. The James Webb Space Telescope has also created deep field images. Its deep field images went even deeper into space and detected objects that are even closer to the Big Bang event. At that time, the universe was more chaotic, with high-energy events like supernova explosions occurring more frequently. Studying these high-energy events is important in understanding the past and present of the universe. But detecting these events from such a far distance was not easy. Let's go back in time, one final time, to November 1895, when a German physicist named Wilhelm Röntgen was investigating cathode rays that were created inside Crookes tube. Cathode rays are streams of electrons emitted by a negatively charged electrode. In the investigation of cathode rays, Röntgen completely covered the Crookes tube with black cardboard to prevent the light outside of the tube from interfering with the beam he was looking for outside of the tube. He was trying to determine if the cathode rays could go through glass. To his surprise, a fluorescent screen about a meter away started to glow whenever he turned on the Crookes tube. This not only indicated that the beam coming from the Crookes tube could go through the glass, but it could also go through the black cardboard. This behavior was inconsistent with what was known about cathode rays. After further experimentation, including having the beam pass through books, Röntgen concluded that this beam was not a cathode ray beam. This beam was an unknown kind of beam, and because of its unknown nature, he called this beam X-ray. Since then, X-ray has been applied to many fields of science, the most notable one being medical science. The use of X-ray is also prominent in material science, microscopy, high-energy physics, and more. The high-energy nature of X-ray interested the U.S. Navy when, starting in the 1920s, they wanted to use the ionosphere for shortwave communications. The ionosphere can reflect shortwave radio signals. Since this layer of the atmosphere is one of the outermost layers of the atmosphere, it's severely affected by radiation from space. A reliable use of the ionosphere requires studying how ionizing radiation from space, like extreme ultraviolet and X-ray, affected it, and thus the field of X-ray astronomy was indirectly born. An X-ray view looks a lot different than anything seen in visible or infrared light. The X-ray view will show only the hottest celestial objects with temperature in the millions of degrees. These high temperatures are caused by a strong magnetic field, very powerful explosion, or a strong gravitational field. The brightest source of X-ray comes from stars that are big enough that when they explode at the end of their life, they create a supernova. For a brief moment in time, the collapsed star grows over 1 billion times brighter than the sun. Earlier X-ray observations were conducted using a rocket on a suborbital trajectory. Because of this, observations were limited to only a few minutes. In the 1970s, X-ray astronomy took a great leap forward with the launch of the Uhuru X-ray satellite by NASA. Since the satellite was in space and above the X-ray absorbing atmosphere of the Earth, longer observation of X-ray sources could be made. With longer observations, we're able to detect variation in the X-ray source. When we then overlaid the X-ray image over an optical image from the same area, we noticed that there were two stars at these locations in a binary system. One is a normal star and the other is a collapsed star with a strong gravitational field. In these systems, matter is pulled into the collapsed star from the normal star. In most X-ray binary stars, the collapsed star is a neutron star. Neutron stars are the end products of the evolution of stars, approximately 10 times more massive than the Sun. These stars underwent a supernova explosion where most of the star was expelled into space at very high speeds. A shockwave analogous to a sonic boom was created from the explosion and spread throughout space, heating interstellar gas to temperatures of millions of degrees. X-ray observatories study these shock waves for clues about the origin of all of the heavy elements from carbon on up. What's left behind after the supernova explosion is an ultra-dense core of the star that's now made mostly of neutrons, a neutron star. And due to the conservation of angular momentum, the highly magnetized core will be rapidly spinning. Matter from the companion star will be streamed onto the neutron star by its strong magnetic and gravitational fields. This will cause the stream of matter to heat up to millions of degrees and emit X-rays. This is how we can also detect black holes. A disk of matter develops around a black hole as matter falls into it. This causes the matter to heat up to millions of degrees, which causes it to emit X-rays. Galactic black holes are also really bright sources of X-ray. They emit as much energy per second as 1,000 or more galaxies. However, their size is only as big as the solar system. Intergalactic gas, in certain cases, can be a source of X-ray also. Even though it is spread really thin, its low density makes it easy to heat and difficult to cool. In regions of the universe where thousands of galaxies are clustered, the intergalactic gas can be heated by them to millions of degrees, causing them to emit X-ray. More research is needed to understand these warm, hot intergalactic medium, as they're also called. There is a constant X-ray background radiation that emanates from all directions in the universe. It's called the cosmic X-ray background, or CXB for short. The source of the CXB is extragalactic and is thought to be the various X-ray sources outside of the Milky Way, but mostly extremely hot gases. During the day, the universe is blocked from our eyes by the sun scattering its light throughout the sky. At night, the universe appears to our eyes as a dark and peaceful place with points of light scattered throughout. In reality, however, the universe is a very active place. We are not able to see that with our naked eyes, but with the help of instruments, we're able to see the things that make the universe very active. Sight beyond vision. In essence, these instruments gives us X-ray vision. I'm Dex DFX for the Celestial Sphere.